class. So today we're going to continue this idea of power series. In particular, we left off with power series of trying to figure out what power series of some functions that we know and love are. The only function we've looked at so far is 1 over 1 minus x. Well, today we're going to ask ourselves the same question. How can we find power series of functions that we know and love? Things like sine of x, e to the x, cosine of x, just regular old functions like that. And in particular, we're going to develop this idea of what's called a Taylor series. And a Taylor series is going to give us a great recipe for finding the power series of any differentiable function. So with that, let's jump into the big picture for today. So in particular today, just kind of the rehash where we've been talking about power series. And power series were still kind of these infinitely long polynomials that happen to represent functions. So we had functions that looked like some function of x equaling this infinite series of some coefficients that depend on the index n of our series times some quantity like x minus a to the nth power. And we started investigating these, asking ourselves if they are functions. Well, we saw that we could differentiate, we could integrate them just using the power rule. We asked ourselves, well, what values of x are we allowed to put into these power series such that we get a meaningful thing in return? A meaningful thing meaning, hey, we put in, say, x equals 3 into this power series. And when we insert x equals 3, we get a finite number in return. So one input gives us one particular finite output in return, just like a functions know and love. And so far in our disposal, all we have is one function who we know what their power series representation is. And using this one function, 1 over 1 minus x, we introduce this notion of stencils, where we could take a power series, replace all the values of x, say with just open parentheses in both the series itself as well as the function itself. And anywhere we had that x, we replace with those open parentheses, and we could just put in those parentheses some other quantity. So say like if we had the function 1 over 1 minus x squared, we could just put an x squared inside those red parentheses. This is what the idea of a stencil was. Well, today what we're going to do is extend these same exact ideas for power series. So everything we've learned for power series still holds true. The only difference is we're going to ask ourselves, how can we actually find the power series for any function? And that's what's going to introduce us to this idea of a Taylor series. As we'll see today, a Taylor series is a recipe for finding the power series of any differentiable function. In particular, there's going to be kind of a slight variation of a Taylor series called Maclaurin series. We're just going to talk about as well. Well, Maclaurin series just is another example of a Taylor series. And well, we're going to look for the power series representations of e to the x, sine of x, and the cosine of x, as well as a function 1 plus x, that quantity raised to some p power, otherwise known as a binomial series. And using these kind of regular functions, we're going to be able to find the power series of other similar functions. So this could be something like, instead of sine, we look for the power series, or in this case, the Taylor series for sine of x squared, functions like this. We can build up functions that look very similar using the idea of stencils, just like we did previously. And then we're going to start asking ourselves, well, what are some applications of Taylor series and power series in general? And we're going to look at some applications revolving around computing difficult integrals, as well as figuring out what some of these infinite series may converge to, using what we learn about power series and Taylor series. And finally, we're going to visualize how adding more terms to the Taylor series also gives us a better approximation to the function itself, just like we did for power series. So again, the big points for today: a Taylor series is nothing but a power series in which we have a recipe to figure out a function's representation as a power series. So all Taylor series are all power series as well. All the tools we've learned for power series so far apply directly to what we know about Taylor series. And with that, let's jump into finding that recipe for Taylor series.